The Heisenberg uncertainty principle is one of the most important concepts in quantum mechanics, introduced by Werner Heisenberg in 1927. Microscope. The core idea. You cannot simultaneously know both the exact position and the exact momentum of a particle. More precisely, delta greater than or equal to 4 delta x delta p greater than or equal to 4 pi h, where delta x equals uncertainty in position, delta p equals uncertainty in momentum, mass times velocity, h equals Planck's constant, 6.626 times 10^34, 6.626 times 10^34 Js. Warning: what it means. This principle isn't about the limitations of measurement tools, it's a fundamental limit of nature itself. If you try to pinpoint the exact location of a particle, like an electron, you lose accuracy in knowing how fast or in what direction it's moving. If you know the momentum very accurately, you can't know exactly where it is. Brain. Why it happens. Particles at the quantum level, like electrons or photons, don't behave like tiny billiard balls. They act more like probability waves, and you can't sharply define both their position and motion because those quantities are spread out in different ways in the wave. Package. Example analogy. Imagine trying to photograph a very fast object in the dark with a flash. The more light, energy, you shine to see where it is, position, the more you disturb it, changing its velocity, momentum. If you don't shine much light, to avoid disturbing it, you can't see clearly where it is. Test tube applications. Quantum mechanics forms the foundation of how atoms and subatomic particles behave. Electron microscopy limits the precision of ultra-small measurements. Quantum computing and cryptography explains why electrons don't crash into the nucleus in atoms. Collision. In simple terms, the universe at the smallest scales is fuzzy. The more you try to force it to behave like classical physics, the more it defies you. Teddy bear. Imagine this. You have a bouncy ball in a dark room. You want to know where the ball is, how fast it's bouncing. But there's a problem. Flashlight. You use a flashlight. To see the ball, you shine a bright flashlight. Now you know where the ball is. But the light hits the ball and makes it bounce in a new direction, so now, you don't know how fast it was moving before. If you try to shine less light, so you don't mess it up, you can kind of see how it was moving. But now you can't see exactly where it is. Brain. What it means. In the teeny tiny world, like atoms, things are fuzzy and weird. You can either know where something is, or know how fast it's going. But you can't know both perfectly at the same time. Package. Real life example. That's why we can't say, this electron is right here, moving at this exact speed. Nature doesn't work that way in the tiny world. It's always a bit of a guess. Cupcake. Super simple version. The more you know where something is, the less you know what it's doing. And the more you know what it's doing, the less you know where it is. Yes. So, today, we're going to talk about one of the most misunderstood yet fundamentally important concepts in the entire field of quantum mechanics. That is, of course, the Heisenberg uncertainty principle. Now, many students, and I've seen this over the decades, believe this principle to be about measurement error, or laboratory sloppiness, or human limitation. But no. It's not that. It is not a limitation of our instruments. No. It is a limitation of the universe itself. Let's begin, then. In classical mechanics, Newtonian mechanics, which many of you are still desperately clinging to like a warm blanket on a cold day, the behavior of an object can be known precisely. That is to say, if you know an object's position and its momentum, which is mass times velocity, you can, in principle, calculate where it has been, where it is, and where it will be. This is a deterministic view of the universe. Laplace's demon and all that. If you know all the initial conditions, you can know everything. But quantum mechanics rudely interrupts this classical dream with a kind of stubborn ambiguity baked into the very fabric of reality. Let me give you the mathematical form first. Don't worry, it won't hurt. Delta. Delta. Greater than or equal to 2. Delta x delta p greater than or equal to 2. Where delta x is the uncertainty in position. Delta p is the uncertainty in momentum. And is the reduced Planck constant, which is /2 h/2 pi, and represents a very, very small number, approximately 1.055 times 10^34 Js. 1.055 times 10^34 Js. Now what does that mean? It means that the more precisely you know the position of a particle, say, an electron, the less precisely you can know its momentum, and vice versa. If you try to pin down where it is, you blur out how fast and in what direction it's moving. If you measure its speed and direction exactly, its position becomes a fog. And no, again, I must emphasize, this is not a statement about the quality of our instruments. This is not a plea for better microscopes. This is not a technological complaint. It is a fundamental feature of the quantum world. It's not that we can't know, it's that nature itself does not allow the particle to have a precisely defined position and momentum at the same time. Let's pause here and digest that. The electron doesn't have an exact position and momentum simultaneously. The uncertainty isn't in our heads, it's in reality. The world at the quantum level is not made of little billiard balls. It is made of probability waves, wave functions. And the act of observation collapses the wave function into one of the possible outcomes. And here lies the heart of the confusion. People think particles have a position and a velocity. But in quantum mechanics, that's not always true. A particle is described by a wave function, which gives a range, a distribution of possible positions and momenta. Now, the mathematics behind this principle comes from Fourier analysis. If you want to describe a wave that is very sharply peaked in space, which means its position is well known, then you need to combine many waves of many different momenta. That is, you need a broad spread in momentum space. If you want a sharply defined momentum, a clean, single frequency wave, then you must accept a very spread out wave in space. This is where the uncertainty arises mathematically. And this is not just true for position and momentum. There are other conjugate variables that obey similar uncertainty principles. For example, energy and time. The more precisely you know the energy of a system, the less precisely you can know when that energy was measured. Yes, it's true. Time enters the party too. Now you might ask, does this matter for real-world stuff? And yes, it does. It explains why electrons don't spiral into the nucleus of atoms, which classical physics said they should. It explains the stability of matter. It puts hard limits on what we can know. It underlies everything from scanning electron microscopes to quantum cryptography. Even more, it shapes our philosophical understanding of reality. The idea that the universe is not entirely knowable, this has deeply disturbed and inspired generations of scientists and thinkers. Einstein, famously, was uncomfortable with this. He said, "God does not play dice with the universe." To which Niels Bohr replied, "Einstein, stop telling God what to do." And Heisenberg, the man himself, quiet, meticulous, brilliant, he didn't just propose a weird idea. He reshaped physics. So to summarize, in the slow, endless murmur that is the fate of all quantum lectures, the Heisenberg uncertainty principle tells us that nature is fundamentally uncertain. The more you know about one part of a quantum system, the less you can know about another. It is not a failure of tools. it is the truth of the universe. Thank you. Sips cold coffee, sighs, stares out window. Would you like the homework now or later?